Hello. I wanted to show a different approach to sketching piecewise defined functions. In this approach, instead of graphing both parts of the function and then erasing, we're going to just go straight to sketching the pieces separately by creating a table of values. So the way this approach works is I'm going to build a table of values here. And what I'm going to do is I'm going to take this information here. Notice how the function changes definitions when x equals 1. So what I'm going to do is I'm going to put x equals 1 twice in the function. Now this sort of seems illegal, but remember it's only really defined at x equals 1 in the second part of the function. It's only defined at x is less than 1 in the first part. So then I'm just going to put in some values here for x. So how about 0, -1, -2, -3, -4, and then how about 2, 3, 4, and 5. And now what I'm going to do is say, well, if I'm left of this boundary, all right, if I'm on that side of the boundary, the function is defined by 3x plus 2, right? Because that's where x is less than 1. And if I'm on this side of the boundary, the function is defined by x minus 3 square minus 4. And so what I'm going to do is I'm going to evaluate the function based on its definition, but only over that subinterval. So for example, when x equals -4 here, I'm substituting -4 into 3x plus 2. So 3 times -4 plus 2, that's -12 plus 2, that's -10. So I'm going to put a -10 here. Similarly, when x equals -3, I'd have 3 times -3 plus 2, that's -9 plus 2, that's -7. And so if I just do that for a few more points here, if x is -2, that would be -6 plus 2 is -4. If x is -1, -3 plus 2 is -1. If x is 0, that would be 2. And if x is 1, we would have 5. But now I'm going to switch over to the other rule. So when x is 1, here I would have 1 minus 3 square minus 4. That's -2 squared, that's 4 minus 4 is 0. If x is 2, we would have 2 minus 3 square minus 4. 2 minus 3 is -1. -1 squared is 1. 1 minus 4 is -3. If x is 3, we would have 3 minus 3 squared is 0 minus 4. That's -4. If x is 4, we would have 4 minus 3. That's 1 squared is 1. Minus 4 is -3. And if x is 5, we'd have 5 minus 3. That's 2. 2 squared is 4. 4 subtract 4 is 0. Now let's look at some other information here. We have the 3x plus 2. We're expecting this piece to be linear. And then the x minus 3 squared minus 4, that looks like a quadratic, a parabola. So just keep that information in mind while we're sketching this. Okay, let's plot some points. I have -4, 10. I have -3, -7. -2, I'm plotting these points wrong. Let's try that again. I have -4, -10. Got to be careful of the signs here. -3, -7. -2, -4. -1, -1, 0, 2, and then 1, 5. Now be careful here. Notice, right? It's only if x is less than 1. So since it's a less than, I'm going to mark that boundary point when x equals 1. I'm going to mark it with an open point. And so what I have so far is this linear piece. Now switching over to the other color. All right, I have the point 1, 0. When x is 1, y is 0. But now again, notice that's defined when x is greater than or equal to 1. Since it's an equal to point, I'll mark that boundary at 1, 0. I'm going to mark that with a solid point. And then I have 2, -3, 3, -4, 4, -3, and 5, 0. And I'm expecting a parabola, so it can't move any further to the left. We'll draw that parabola, or part of the parabola. So this is this other approach by creating an extended table of values and sketching the pieces. Let's see another example. And maybe this would be a good time to pause and try this one on your own. All right, so I'm going to create a table of values here, an extended table. And I see that the boundary changes, or I should see that the function changes at -2. So I'm going to put -2 sort of in the middle twice. And then I'll extend in either direction. -3, -4, -5. How about -6 to the left? And how about -1, 0, 1, 2? All right, let's see what we have here. All right, so negative absolute. Hey, we have an absolute value function. All right, so let's see. If x equals -6, I'd have the opposite of the absolute value of -6 plus 5 plus 2. -6 plus 5 is -1. The absolute value of that is 1. Change the sign. That's -1. -1 plus 2 is 1. If x is -5, I'd have -5 plus 5 is 0. Absolute value is 0. Plus 2 is 2. If x is -4, -4, absolute value of -4 plus 5, that's 1. Change the sign. -1 plus 2 is, that's again 1. If x is -3, let's see, I'd have -3 plus 5. That's 2, the absolute value of which is 2. Change the sign. -2 plus 2 is 0. And if x is -2, we go through the arithmetic here, I'd have -2 plus 5 is 3. The absolute value is 3. Change the sign. -3 plus 2 is -1. All right, now switching color. All right, again, I've got this, what, x squared plus 3. That's again a quadratic. All right, so -2, I would have -2 -2 squared plus 3. That's 4 plus 3 is 7. Substituting -1, I would have -1 squared plus 3. That would be 1 plus 3 is 4. All right, substituting 0, 0 squared plus 3 is 3. Substituting 1, 1 squared plus 3 is 4. And 2 squared plus 3 is 7 again. And again, I'm expecting a parabola from that. Okay, let's plot some points here. I have -6, 1, -5, 2, -4, 1, -3, 0. Now, -2, -1, let's be careful here. At -2, -1, remember, x is less than or equal to -2. So I'm going to use a solid point at -2, -1. I'm expecting that V shape. So if I sort of extended, sorry about that. If I extended this a little bit, plotting a few more points, I'd expect to see this V shape. ending there. And now for the x squared plus 3, plotting the points we have. Now again, careful here, it says, right, x is greater than -2. Since it's a greater than, I will use an open point at -2, 7. And then plot the other points, -1, 4, 0, 3, 1, 4, 2, 7, and I'm expecting that parabola shape. And so I'll draw that. So again, this was another approach to sketching piecewise defined functions. I hope you find it useful, and just another way to look at how to sketch these types of functions.